Well, good morning, everyone, and let's continue our study of collider physics. So, in the previous lecture, I described the parton model. So this was the idea that you can model the proton, or another hadronic initial state, by means of what I called parton distribution functions. Or PDFs. So the idea was that we consider, for example, at LHC, a highly boosted proton. That proton contains lots of quarks, antiquarks, and gluons. And the way we're going to treat it is that any individual particle in the proton has a momentum which is equal to some fraction x of the total momentum of the proton, with x a number between 0 and 1. We described the probability of finding such a particle. We took this momentum to be, in the last lecture, exactly collinear with the momentum of the proton. We then described the probability of finding that object in terms of functions fi of x dx. So the d probability has this form, and that gave us Feynman's parton model. Within the parton model, we can then calculate whatever cross-sections these particles have, sew them up with the PDFs. The PDFs we have to obtain experimentally or obtain by actually solving QCD at large distances. But in any event, typically today one obtains the PDFs very accurately by using some data to determine them, and then once determined, you get predictions for other reactions. The model is quite idealized. In particular, there's no transverse momentum assigned to the partons, even though the proton has a finite size, so there must be some momentum uncertainty of the partons in the transverse direction. But when we talk about scattering processes that involve, let's say, 100 GeV of transverse momentum, that kind of contribution to the momentum of the parton is a very small effect. On the other hand, there are other effects that can put the partons out to very substantial transverse momentum, and those have to be taken into account. On the other hand, it's not so hard to take those things into account, because in order to give a parton a momentum transfer which is large, let's say 10 or 20 GeV, we're now in the weak coupling regime of QCD, so we can evaluate those large momentum transfers by using QCD perturbation theory. And so in the previous lecture, we had talked about processes of the following structure, where two partons would come in have a hard scattering cross-section and go out, and we thought about these partons as having momenta that are exactly aligned with the proton beam direction. Now I'd like to introduce some QCD correction to that, which will allow the partons to have a transverse momentum with respect to the beam axis of the protons. So the simplest process that you might imagine doing that, let's say we have a quark that goes into a hard reaction. The simplest process that you might imagine is the quark now emits a gluon, and then the quark and gluon recoil against one another and balance their transverse momentum. And so what I'd like to do to start this lecture is just to compute this contribution to the hard scattering cross-section using a reasonable set of approximations, and try and see what physics there is in this kind of process. So it's not so hard to do this, but maybe there's some remark that I should make that it's actually really important to take this effect into account. So you folks are used to calculating ordinary processes in quantum electrodynamics or maybe in QCD. And you have some kind of feel especially if you studied QED, for what happens when you have a massive particle that radiates photons. And QED and QCD are not so different in this respect. So you can imagine what happens if you have a very massive quark that radiates a gluon. There's a singularity when the gluon is soft, which you folks, I hope, have studied how to take into account. And then the behavior is kind of smooth with respect to the various angles at which the photon or gluon can be emitted. However, at high energy, there's another consideration that comes in, which is going to be very important to us, which is that when you ignore the masses of the particle, when you think about a massless particle, or something close to a massless particle, splitting off a quantum of radiation and going forward, there's another kind of singularity that comes in that enhances the effect of a certain kinematic regime. And this is going to be more or less the central feature of the physics I'm going to describe in this lecture. So if you think about it, if you have a light-like particle with momentum p00p, and you split that particle in whatever way into two parallel light-like vectors, let's call this one z, and this one will have momentum 1 minus z. And everything is massless. These two particles end up on mass shell, both of them. In a diagram like this, I can have an incoming quark with this momentum. I can radiate a gluon, and if that gluon has its momentum parallel to the direction of the incoming quark, the two momenta of the final gluon and the final quark split like this. Ordinarily, you would say that quark is off shell, and there's some suppression for that. But actually, if the gluon is exactly parallel to the incoming quark, the quark is on shell, and the denominator of this propagator vanishes. So then we're going to get infinity. And we have to deal with that infinity the way we deal with other infrared infinities that we find in quantum field theory. A given diagram will be infinite, but when we sum over all processes, we'll have cancellations and have a finite value. Nevertheless, what you can see is that the radiation of gluons in the forward direction from a massless quark is going to be enhanced. And so that's going to be a feature of the calculation that I'm now about to do. So, question? There was a question. Or somebody just waking up. That's fine. Okay. So let's now try to use this kind of intuition and make an approximation to the amplitude for this diagram. So throughout this lecture, there's going to be some kinematic situation where a quark of momentum p radiates a gluon of momentum q and turns into a quark of momentum k. And so we're interested in the collinear limit of these situations. And that's going to come up again and again in this lecture. So let me just introduce some notation for that. P is equal to E, 0, 0, E, so I'll align it with the 3-axis. Q is going to carry away the momentum fraction 1 minus Z, and it'll have some transverse momentum. So let's work in the 1-3 plane as I've been doing before. And the momentum k is then z pt ze. And so what happens is that this quark will reduce its energy and momentum by the factor z, with the rest of it being carried off by an almost collinear gluon. Okay. Now, we should be just a little more careful than that. And so let me write these vectors now in a way that's slightly more appropriate to this situation. P is equal to E, 0, 0, E. The gluon is on shell. So I'd better take care of that by adjusting its longitudinal momentum to first order in PT. So to the leading order in PT, this is now an on-shell vector. And momentum is conserved. So the momentum of the quark is now this, ZE plus PT squared over 2 times 1 minus Z times E. And now we're in a situation where we can evaluate K squared, which is the denominator of this propagator. So this propagator, I'm going to write UU bar divided by K squared. And when I compute K squared, I'll have ZE squared minus PT squared. The propagator, please notice, has a space-like momentum, minus ZE squared minus PT squared times ZE over 1 minus ZE. These cancel. These cancel. Everything is proportional to PT squared, so if these vectors were actually parallel, I would get 0. And as you see, what I in fact get is this expression, PT squared over 1 minus Z. So to the extent that either the transverse momentum carried by the gluon is very small, or, well, just that. If the transverse momentum carried by the gluon is very small, this line here is almost on shell. And I can regard this process as its own parton subprocess. And this process is something that I'm adding to that. So with that intuition now, we can go through and make some kind of accurate calculation of what's going on here. So let's now try to do that. This is some matrix element of the kind that I discussed yesterday. What I'm now interested in is the matrix element for this gluon emission, which is G sub S, U dagger of K. Let me imagine that I have a left-handed here, a left-handed quark radiating a gluon. By by P, the squared amplitude is going to be the same if I change all the left-handed things to right-handed things and vice versa. So let's just work with left-handed particles. U of P. And now that's pretty straightforward. Let's calculate this amplitude. The spinors that we need are UL of P is the square root of 2E times 0, 1. And UL of K is the square root of 2E times Z. And then the spinor is rotated slightly because this vector has some small transverse momentum. So using the formula that I gave you, I guess in the first lecture, PT over 2ZE and 1 here is the approximation to first order in PT. And it turns out that for what I'm doing today, it's perfectly sufficient to work just to first order in PT to calculate this particular amplitude. Okay. The gluon polarization vectors, these are massless particles, so I only have to look at the left and right-handed polarization vectors. And those will be 0 cosine theta, which is 1 in this approximation, minus or plus, plus or minus I if I put left and then right. And then over here, PT divided by ZE. So those are all the polarization objects to the, 1 minus ZE. Those are all the polarization objects to the appropriate order in PT that we have to work. Okay, so now we can just plug all these things into here and start computing amplitudes. So first of all, Let's consider the amplitude for a left-handed quark to split off a right-handed gluon, turn into a left-handed quark. That would be I G sub s. There's a 2e. There's a square root of z. Good. There's this spinner that appears here. The sigma dot e combines with this in such a way that I get, oh, I'm sorry, there's a 1 over the square root of 2. A 2 here and a 0 here. And then the spinner over here is this one, it's 0, 1. So these two elements are small. They come from this. It's pt over 1 minus ze and pt over 1 minus ze with a minus sign. They don't really matter. The only contribution that matters is, oh, sorry. I'm very confused. They do matter. The only contribution that matters is that times that, which is going to give us minus I G sub s, 2e, so the square root of z, 1 over the square root of 2, pt over 1 minus z times z. And so that's extremely simple. And frankly, it isn't going to get much harder in the rest of this computation. Okay. So the next thing we can do is to compute the matrix element for a left-handed quark to emit a left-handed gluon. And that's given by the same expression. The same spinners. The only difference is that the 2 is now up here instead of being down here, as you can check. And then there are two contributions. The first one is the one that I wrote here. And the other is the one that I get by taking that times the entry here, which is minus pt over 2ze. So I took the minus sign out in front. There's just a ze, and the 2 cancels the 2. Well, now we're in fantastic shape. Because now, as you see, we have very simple expressions for the emission amplitude here, and then we can just try and combine that with the expressions for the other aspects of this. In particular, let me just calculate the matrix elements summed over the two gluon polarizations. That's G sub s. The e's you see are going to cancel. There's a factor of 2 left over. There's a z left over. There's a pt squared, and if I combine these, there'll be a z and a 1 minus z that gets squared, and then the z is not present over here, so let me account that in this way. This is the contribution from a left-handed gluon and a right-handed gluon. Okay, that's really easy. Now, I'd just like to put this together with the rest of the process that I had sketched on this blackboard, and we'll try and calculate the result for a complete cross-section. So once again, we have something like this, and so now let me try and write the result for the cross-section, which corresponds to this diagram. So let me preserve over here, k squared is equal to minus pt squared over 1 minus. So what we have is the cross-section for, this is a quark, this is something, let's call it x, let's call what's out here y, and the process will look something like this. The cross-section for pp going to a gluon plus what I've called here y is equal to, well, first of all, there are the parton distributions for the incoming factors. I think in the notes this is called 1, and sorry, this is called 1, this is called 2, and this is called x, so please excuse me. F1, the integral dx2 f of x2. Then we have a cross-section, so there's a 1 over 2s, there's an integral over phase space, which includes the integral over the gluon momentum, the integral over whatever phase space there is for x, and there's a momentum conserving delta function, which is P1 plus P2 minus P of the gluon, which is Q, minus Px. And then there's a matrix element, which is the following. First of all, this matrix element then the propagator here, we've already actually used up the u in that propagator, so what should appear is 1 over k squared squared. So that's pt squared over 1 minus z, the quantity squared. And then finally, whatever the matrix element is for this process, which I'm just going to write as m of the quark of momentum k plus 2 going to x. Okay. Well, now we're in excellent shape. As long as pt is small, there's a very strong singularity here. And I'm computing basically the coefficient of that singularity. So let's just continue now. The first priority is to try and organize the phase space in the right way. And so to do that, let's write the integral d3q over 2 pi cubed times 2q. And there's also this factor of 1 over s out in front in the following way. First of all, I'd like to write this as by writing d3q is the integral dz times e, that's the longitudinal component of q, the integral d2pt, that's the transverse component of q. In the denominator there's a 16 pi cubed. There is a q, which is 1 minus z times e. And this 2s I can write in the following form as 1 over 2zs, which is the s hat of the subprocess where the quark is, this quark here, is now interacting with number 2. And then there's a factor of z in the numerator. Well, now we're doing excellently, because now we can plug this expression into there and see what we get. So first of all, there are these integrals over 2 parton distributions. We'll worry about that in a minute. There's also an integral dz, and I'm going to write this integral here as dpt squared times pi divided by 16 pi cubed 1 minus z. Please notice that the e's are canceling. there's a factor of z here that's left over that we need to take into account. Now, there's an integral of the x phase space and a momentum-conserving delta function that I can now rewrite as k plus p2 going to px. And then there's a matrix element, which is the matrix element over here. And there's a factor of 1 over 2s hat, which came from there. Okay, this is fabulous because this quantity here is the cross-section for the subprocess, where the quark and whatever's coming from the other side make whatever hard process there is. And then finally, there are these various factors that are left over. G sub s squared, there's a factor of 2z, there's a factor of pt squared over z squared times 1 minus z squared, there's a 1 plus z squared, and there's the denominator, which is 1 minus z squared over pt to the fourth. Now you see some nice things are happening. We can separate out the cross-section for the subprocess where the quark with momentum k hits what comes from the other side and makes x. So there's a sigma of k plus 2 going to x. There's left over an integral over z. There's an integral dpt squared over, let's see, from this 16 pi and the 2, I can eat up some factors and get alpha s over 2 pi. There are various factors of z and 1 minus z that are canceling here. So I'm going to get a 1 plus z squared divided by z as the leftover thing. And let's count the factors of pt. There's a dpt squared here. There's 1 in the numerator and 2 factors in the denominator. So it's pt squared over pt squared. And, and some parton distribution integrals that I had left out. Okay. So this is finally pretty cool. I have the hard cross-section for the quark after the gluon emission convolved with something, and that gives me the cross-section for the process that I'm interested in. So we're now in a situation where we can try and take this whole thing and try to interpret it as a parton distribution. What's going on the 2 side is irrelevant. Let me take that out. What's going on the 1 side is the following. The integral dz, the integral dpt squared over pt squared, alpha s over 2 pi. Oh, good Lord. I made a bad mistake. I left out, when I computed this cross-section, the color factor. There's a TA here, and when you square it, you get a 4/3. And please forgive me for leaving that out. So that should go with the alpha s. This momentum structure, 1 plus z squared over, this should be 1 minus z. Please excuse me. Yes. And then the integral dx1 of f1 of x1. And then we have the hard cross-section. So this is xzp times 2 goes to x. So then the last thing that we have to do is to replace xzp, which is the momentum of the quark that's going into the hard process, by some new variable, let's call it x prime times p. So x prime is equal to xz, or here, I'm getting way ahead of myself, I'm sorry. Yeah, let's call this w. So then dx1, which appears here, is equal to dw divided by z. And so if I make that change of variables, I now have, for the expression that I'd written here, the following expression. The parton distribution on the 2 side, which we have not messed with, a parton distribution on the 1 side, which I'm going to write like this. dw, which is now the momentum fraction of that incoming quark, the integral dz over z, because this factor comes from here, dpt squared over pt squared, 4/3 alpha s 1 plus z squared over 1 minus z. And then the parton distribution f1 evaluated at w over z. That's this factor here. And then finally the hard cross-section. Okay. Well, this is very nice, because what you see is the structure here is exactly the same as I wrote last time, except for this factor here, which you can see is now interpretable as a correction to the parton distribution on the left-hand side. And so now what we've managed to prove is the following. In the approximation where we look most carefully at this singularity here, which is a 1 over pt to the 4th when we square it singularity, we can represent this process by considering this emission here as part of the parton distribution of the proton. And we have a correction to the parton distribution of the proton, which I've actually calculated explicitly here. So let me write that out in a more careful way. We found that f1 of x is turning into f1 of x plus the following factor, four-thirds alpha s over 2 pi, the integral dz, the integral dpt squared over pt squared, please excuse me, over z, the kinematic factor that I wrote there, 1 plus z squared over 1 minus z, and then here appears f1 evaluated at x over z. So whatever parton distribution for the quarks we had here, we've now modified it by this gluon emission. The modification is large because, please notice, there's a singularity here. This is actually a modification that's formally going to infinity as pt goes to 0. So this is going to be a large effect. And it's an essential effect in the calculation of the parton distributions. If you were to do that integral, we can now ask what are the reasonable bounds over which we could evaluate that integral. So there are two limits, an upper limit and a lower limit. The lower limit is where we get into the proton structure, and this gluon here is emitted very softly. So the lower limit at this calculation is something like the mass of the proton. The upper limit is set by the hardness of this interaction, Q. If this interaction gives a momentum transfer Q, what we need to assume about this process is that the momentum carried off by that gluon is small compared to Q. Otherwise, we start changing the kinematics of this process, which I had assumed is just what we had before. And so the upper limit here is q, and so this factor now has the following form: a logarithm of q squared divided by the mass of the proton squared times the kinematic factors that you see here. Now, actually, this is really a large effect. It's an effect that's not in perturbation theory. It's outside of perturbation theory. Because let's think about the high end of this integration region. So at the high end, the alpha s is a value of alpha s that's being evaluated at q, the momentum transfer of this process here. And on the other hand, there's a logarithm of q. So alpha s of q is something like pi over b0, the log of q over lambda. And this thing is the log of q. And the logs of q are canceling. And the log of q is the only thing that keeps alpha s small. So this is order 1. The possibility of collinear gluon emission from the quark as it goes into a hard process is an order 1 correction to the parton distribution. And we just need to be aware of that and take it into account anytime we talk about parton distributions. Well, now as you see, it gets worse. Because if I can radiate one gluon with order 1 probability, then I can radiate another gluon with order 1 probability, and so on and so on. And so if I want to do an order 1 calculation in QCD of the rate of this hard scattering process, I'd better be able to take into account an arbitrary number of gluon emissions on this side, and needless to say also an arbitrary number of gluon emissions on this side. All of those gluons, to get the enhancement, being in the collinear region, where the angle between the gluon emission and the initial quark is very small. So we'd better have a process for taking into account not only the leading order term, but all the higher order terms. Now, fortunately, the leading contribution comes from a regime which is pretty simple. Because in each case, if I have a hard gluon emission here, that is a large angle emission, I really change the kinematics. I knock this guy far off shell, and then everything else changes. So the only regime where I get the full singularity and the large enhancement that I'm talking about is the regime where the innermost PT, PT1, it's got to be less than Q, which is the momentum transfer in the hard process. PT2 has to be less than PT1. PT3 has to be less than PT2, et cetera, et cetera. So what we're really set up here for is an evolution process in the hardness, the transverse momentum liberated by these gluons. If you like, you can think of the quark coming out of the proton almost parallel with the proton direction. It gives off a small PT gluon, then a harder PT gluon, then a harder PT gluon. But in each case, the total transverse momentum that it's gotten is smaller than the transverse momentum eventually delivered in the hard process. Okay. Well, now I think that gives a clue as to how we're supposed to do the accounting. What we should really do is to think about this as an incremental change in the particle distribution over each interval of transverse momentum. And so I can think of this as a delta F1 if I integrate only over a small region from, let's say, Q to Q minus delta Q. And then this becomes the kernel of a differential equation, which then the parton distributions will satisfy. So that's a very important differential equation. For the specific case that I'm talking about here, it was first written down by Gribov and Lopatov. And the full theory in QCD later given by Altarelli and Parisi. and by Dochschitzer. And I think I like to call these the Altarelli-Parisi equations, although sometimes you see them called the D-Glop equations. And for just the physics that I've given here, the equation would be like this, that the quark distribution of x, d by dq squared, is given by, so here's the logarithm, everything else on this side. 4/3 alpha s, which we should now evaluate at q, over pi, the integral dz over z, the kinematic factor that I had shown there, and the quark distribution at a slightly higher value of the energy fraction. These parton distributions now become functions of Q. Yesterday, remember, they were completely independent of Q, but they are functions of Q only on a logarithmic scale in Q. So it's possible that if your range of momentum transfer is sufficiently narrow, you might miss this dependence. And that actually, historically, fortunately, was true for the deep inelastic scattering experiments at SLAC that I told you about yesterday. But over a long range in Q, this becomes a very important effect. And I remind you that from the deep inelastic scattering experiments, which occurred at Q of order 1 GeV, to the LHC, where we're talking about Q at the level of hundreds of GeV or even TeV, that is a sufficiently long range in Q that this kind of evolution equation becomes very important. So interesting. This is something that I didn't tell you about yesterday, but it's absolutely essential when you talk about the form of parton distributions. And now I guess we just have to complete the formalism and write down the full set of Altarelli-Parisi equations. Okay. So, are we done if we just consider this particular kind of collinear splitting? And if you think just a moment about QCD, you see that that's not correct. First of all, here I have the quark, the split quark, as the part that goes into the hard process. But you could just as easily have the split gluon as the particle that goes into the hard process. So you can think of the collinear splitting as generating a gluon distribution by an equation very similar to the one that I wrote here. Similarly, if I have a gluon parton, that can split into quarks. And I can generate some new part of the quark and antiquark distribution from gluon splitting. And then finally, the gluon can split to gluons. And this also affects the form of the gluon distribution. What it does is to take a gluon at high momentum fraction in the proton and turn it into two gluons that have somewhat smaller momentum fraction. In both this process and these processes, please notice this denominator here. The probability of emitting is 1 over z of the gluon divided by z of the gluon. That's the soft singularity that you folks have seen before in quantum electrodynamics. And so whenever you have splitting off of a gluon, either from a gluon or a quark, that tends to accumulate partons at small values of z, or eventually small values of x. And so that's also going to be a feature of the evolution that we describe. So with that in mind, let me now write down the full set of Altarelli-Parisi equations. And I'm not going to derive the other kernels for you, but actually it's a very easy and fun exercise using these two-component fermions. And I really hope that you folks will do it either at the school or when you get home. So let's now write the full set of equations. D by d log q of a quark distribution is alpha s of q over pi dz over z, what's called the Altarelli-Parisi splitting kernel, q to q of z, f sub f of x over z, plus, since a gluon can split to a quark, there's another kernel that we haven't computed yet with the gluon distribution appearing here. This term here accounts this process that I had drawn. The same thing for antiquarks. With the same kernels. And for the gluon, the following structure. First of all, any quark can split off a gluon. So there's a p gluon from quark. The sum over f and ff of x over z plus f bar of x over z. And then also the gluons can split to gluons with the gluon distribution. Okay. And then we need to know what all these splitting kernels are. So one of them I've already derived for you. The pq to q is 4/3 1 plus z squared over 1 minus z. And there's something else which we're going to talk about in a minute. The gluon from a quark is just the opposite of this, turning z into 1 minus z. And some of you might know this particular distribution as the Weizsäcker-Williams distribution, the distribution of photons that you get when you look at the initial state emission from an electron in quantum electrodynamics. The quarks that come from gluons, it's a half z squared plus 1 minus z squared. And finally, the p gluon from gluon is a little more complicated. This is a somewhat unconventional way of writing it, but it's the one that's most easily derived using two-component spinners. Yeah. And then there are some extra terms that appear in these equations that I need to explain. First of all, I'm going to put a little plus here and here. Then there's a 3/2 delta of 1 minus z that appears here, and down here an 11/6 minus, please excuse me, nf over 9 delta of 1 minus z that appears in here. Okay. So as I said, this one follows trivially from that one. These two are new expressions for which you have to do some similar Feynman diagram calculations. But you notice that the one I did for you was just really easy. And so in the same way, it's very easy to derive this equation with some simple calculations using the polarization vectors that I had written for you. Okay, the one subtlety that I need to explain are these extra terms that appear here. And I think probably it's easiest to explain if I talk about this term here. So what we calculated a moment ago was the change in the parton distribution at lower values of x when I have a high momentum quark that emits a gluon and turns into a low momentum quark. But in order to complete this calculation, I ought to also realize that I'm not changing the number of quarks. The high momentum quark goes away and the low momentum quark appears. So in addition to the contribution that I wrote for you explicitly, where you would introduce the lower momentum quark, we have to remove the higher momentum quark. And so that would take the form in these kernels of a delta function contribution at z equals 1. A way to figure out how that contribution works is to insist that the quark to quark splitting function should obey this identity so that the total number of quarks is not changed by that process. The way this is normally done in the literature is to introduce a distribution called 1 minus z plus, which is defined in the following way. The integral dz from 0 to 1 of f of z over 1 minus z plus is equal to the integral dz from 0 to 1 of f of z minus f of 1 divided by 1 minus z. So this integral is now finite when z goes to 1, and you can just evaluate it. A way of thinking about this plus distribution is that it's the limit as epsilon goes to 0 of 1 over 1 minus z, cutting out the region of size epsilon around 1, and then introducing a delta function term proportional to this integral up to 1 minus epsilon. Okay. So the little plus here, which looks very innocuous, is actually a divergent delta function term. But writing it in that way kind of simplifies the presentation. If you then evaluate this quantity here, I think that's actually the way to write it, what you'll see, the explicit calculation is in the notes, is that it actually does satisfy this sum rule that you have. Okay. By the way, if any of you folks write a computer program that implements the Altair-Parisi equations, you don't have to define the distribution in either of these ways. You should do it in the way that makes the computation most numerically stable. But these are just some ways of representing that particular distribution. For the gluons, we have a similar situation. When the gluon turns into two gluons, we get these two gluons here, but we lose the gluon at high momentum. And so in the same way, the gluon distribution has to have a delta function, a negative delta function of 1 minus x in it. And you can check that this is the right way to do it. The thing to check is that the momentum sum rule for gluons is satisfied. So we remove one gluon, we add two gluons, but we don't change the total momentum of gluons. And you can check that the momentum sum between this term and that term vanish. This term is a compensation for the effect of a gluon turning into quarks. And please notice that it's proportional to NF, which is the number of quarks sufficiently light that they act as massless particles in the interaction. So if Q is about 10, you would include U, D, S, and C, but not B in that part of the equation. Okay? So, these are the famous Altair-Parisi or DGLAP kernels. They appear more or less ubiquitously in collider physics. And aside from these delta function 1 corrections, which are a little hard to remember, this is something else that if you want to be a collider physicist, you should probably commit to memory and have the forms at your fingertips when you need them, because they just come up all the time. Okay. The next thing I'd like to do is to talk a little about the implications of these equations for the parton distribution functions of the proton. So there are three distinct effects that if you start looking at these equations, you're going to have. Maybe I should have said, how are we supposed to now fit parton distributions in the proton, given that those distributions are changing from one value of Q to another, from one scale to another scale? Well, there are two ways to do this, one of which is the way you would think about it, and the other is the way that you would actually do it in practice. The way that you would think about it is you would imagine that you could totally solve for the wave function of the proton. Then you would have parton distributions of the kind that I talked about yesterday in some kind of intuitive form. So you have a valence distribution, which looks like this. a gluon distribution that probably looks like this as a function of x, and a C distribution for quarks and antiquarks that looks something like that. Now, what happens to these distributions when you integrate the Alterelli-Parisi equations from low Q to high Q? Well, you can look at the equations, or we can just follow the physics that goes into those equations. The valence quarks are going to emit gluons, and so the valence quarks then, if this is the value for, let's say, Q equals 3, by the time you have Q equals 300, they're going to come down to much lower values of the momentum. What happens then is that that action increases the number of gluons. So the gluon distribution, which might look like this at low Q, starts looking like this at high Q. And finally, the gluons split to quarks and antiquarks. So this distribution roughly gets steeper and grows enormously as Q increases. And maybe I should say, all flavors of quarks that are light at that value of Q can be involved. So I think people are surprised by thinking how much charm and strange there is in the proton when you get to the LHC. And that's the result of the gluons here splitting into CC bar and SS bar, which can then be the initial states of LHC hard processes. Gluons can also split substantially to B. And so it's very interesting to think about LHC processes where you use the B partons in the proton to initiate reactions that involve the third generation. And when we get to the 100 TeV collider of the future, we'll also have top quarks as partons in the proton generated by these equations. Now, that's how you would do it intuitively. What do you do in practice? Well, in practice, what you do is that you make a kind of a free model of the parton distribution, introducing, let's say, 5 or 6 parameters per distribution. You would write a parametrized set of equations that represent the parton distributions at one value of Q. You then use the Alterelli-Parisi equations to evolve that parton distribution to a number of values of Q appropriate to different experiments. For example, Q of order 1 or 3 to fit the old SLAC data, Q of order 30 to represent the muon proton and muon nucleus scattering data generated at CERN in the early 1980s, Q of order 100 or hundreds to represent the electron-proton data that was generated at the HERA collider that I told you about yesterday at DAISY. And so for each data set, you fit these same parameters, and eventually by doing a global fit, you arrive at an understanding, which now always has to be dynamical in Q squared, of the shape of the parton distributions. So let me just give you some examples of that if you look at the figures. In figure 1, you remember there was this quantity F2 of x that I wrote down in the previous lecture. So F2 of x, which is now a function of Q, is the sum over the quark flavors, QF squared x times FF of x plus F bar of x, now as a function of Q. What happens to f of x, F2 of x as a function of Q, are just the effects that I've described here. The valence contributions down, and so at large values of x, the function should decrease. The C contributions get much larger, so at the small values of x, the contribution should increase. And in figure 1, I have basically the world data set for F2 of x and Q squared as compiled by the particle data group. And you see exactly those effects. A decrease in all the functions at the bottom, which correspond to the large values of x, and a significant increase, especially measured by HERA, at small values of x. If you turn the page and look at figure 2, you can see the fit that was done to the Hira data at very low values of x. This goes down to x of 10 to the minus 4. And at those small values of x where it's all c, you can see there's just a dramatic rise when you go from q of order 1 to q of order 10. And that's all generated by Alterelli-Parisi evolution. So the qualitative effects predicted by QCD in those parton distributions actually are seen in the data. Now, if you make a global fit to the data, there are several groups that are doing this. These are really dedicated groups, for the most part, that have decided, people have decided this is going to be my career, I'm going to work on this for decades. One of them called, in various incarnations, the current incarnation is MSTW. Martin, Sterling, Thorne, and Graham Watt is now the custodian of it. In England, there's a group in the US called CTEC. CP Yuan at Michigan State is the custodian of that now. And mainly in Italy, I guess, there's a group that makes a neural network model of these PDFs and then fits the data associated with that model. So in the latest particle data group review, they show the results of what the parton distributions look like from this neural network model fit, and I put that in figure 3. And you can see that these effects are pretty much as I've described. On the left, you see the low Q. On the right, you see the high Q. These are outputs of the same fit, the valence, C, and gluon distributions. The gluon distribution is always divided by 10. There are a lot of gluons in the proton. The gluons carry roughly 50% of the total momentum of the proton in the parton distributions. So those figures you should spend a lot of time studying. They have basically in them all the physics that I've just tried to describe, and these are all now the inputs, what you're seeing in the LHC beam to initiate a hard reaction. Okay, now once you have these distributions, you can then try to compile luminosity functions, which you can then use to estimate the rates of reactions at the LHC. And I think I'm going to skip this because we're running a little late, but it's described in the lecture notes. And there's a very nice presentation of this in the textbook by Ellis, Sterling, and Weber. So those people define luminosity functions. That is, given two protons colliding at a certain energy, quarks, gluons, and antiquarks are coming out. And you can describe the partons in terms of the luminosity for quark-quark collisions or quark-gluon collisions in that process. And with maybe, I should say, not the most current set of parton distributions, but still a very useful one, Ellis, Sterling, and Weber made some graphs of these. And I encourage you to look at them. They're in the notes for all of these cases. A very interesting aspect of these graphs is that as the center of mass energy here becomes less than the center of mass energy of the PP reaction, there's a kind of scaling, a straight line on a log-log plot for these parton luminosity functions. And there's a rule of thumb that goes along with this, that a factor of 2 in energy equals a factor of 10 in luminosity. So if you have a factor of 10 higher luminosity, you can access cross-sections that are a factor of 2 in energy higher, or vice versa. So, well, I presented those in these notes, and you folks can look at the pictures and study them. Again, when you go through these pictures, there's a lot of physics in them, and you should really try and study and understand all the details that are coming out of these calculations. Okay. So now to turn attention, so far I've only been talking about gluons, collinear gluons and quarks emitted in the initial state of a proton-proton reaction. But in the same way as we've discussed the initial state, the same physics takes place in the final state. And so let's now turn our attention to that question. So you've all memorized these distributions. I'll erase them. So now the process we want to consider is the following. We have our protons come together. We initiate some parton-parton reaction. Some quark comes out of that reaction with momentum p. It's still an extremely relativistic, essentially massless fermion. It can still radiate a gluon. And in fact, the matrix element for this process is the same as that we described over here. And in fact, the kinematics is almost identical with just some very small modifications. So for the same reasons that I just discussed for you, this is an order 1 effect in QCD. And so as we develop the final state of a hard scattering reaction, we're going to have large collinear emission of gluons and quarks from whatever comes out of that reaction. The logic is just the same, just a few details are changed. And so let me sketch this out for you as well. So once again, I'm going to start from those momentum expressions that I've written there. So I'm going to try and get the distribution of the final quark after gluon emission, considering an initial quark that's coming out of a reaction. Q is on shell. And let's say that it recoils with momentum pt. K, please notice in this kinematics it's also on shell. And P is off shell, and its vector is determined by momentum energy conservation. And the sum of these two things, so that's Z times 1 minus Z, E times 2. Okay. So the off-shellness of this propagator is now PT squared divided by Z times 1 minus Z. It's still true that if the emission is perfectly collinear, the off-shellness goes to 0, and we get a singularity, which is very important for the same reasons that the initial state singularity is important. So now we can just go through to calculate the cross-section for this process. And when we compute that cross-section, it's the same matrix element, because I only needed that to leading order in PT. So let me just write that down for you again, hopefully correctly this time. Did I get that right? Yes. Okay. Okay. So now we go through the same tricks that we did earlier in the lecture. We have x plus, let me just use the same notation as in my notes. AB going to x plus a quark of momentum k plus a gluon of momentum q is equal to 1 over 2s, whatever the phase space is for x, d3q over 2 pi cubed d3k, and an energy momentum conserving delta function. Okay, then the matrix element, which is given by the matrix element for A plus B goes to X plus a quark of momentum p, the propagator, which is 1 over p squared squared, and the matrix element for p goes to q plus k, summed over the gluon polarizations, which is the thing that I wrote down over there. Once again, we need some simplification of the kinematics appropriate to the collinear region. So it's, I think, most convenient to notice that K is equal to P minus Q. So if I keep Q fixed, I can turn this into a D3P. And so then what we have is the following. D3P over 2 pi cubed times 2E, which is the energy of P, dz times E, now I'm working on the Q integral, dpt squared times pi, divided by 16 pi, 1 minus z E, and then over here there's a K, I stole a Z, so I should put it back. The S is the same, and actually this thing naturally becomes the full phase space integral for the hard process. So we now get sigma AB to x qg is equal to the cross-section for AB going to x plus a quark of momentum p. And then in the final state, we have the integral over z, the integral dpt squared. And now the same rearrangements go on as before. Let me just try and pick up all the factors. So here we have 4 pi times 4 pi. There's a z and a 1 minus z. This factor is the square of what I wrote there. So that's going to give us z squared times 1 minus z squared divided by pt to the 4th. Then there is the matrix element that I've written on the far side of the blackboard, 4/3 g squared 2z and 1 plus z squared over z squared 1 minus z squared. And now you see this whole thing is simplifying extremely nicely. The various factors of z and 1 minus z are almost all canceling, except that there is a factor of 1 minus z left over. There's an alpha s. The rest of the structure is as before. Sorry, I forgot to cross this guy out. And the final result is now the following. This is the cross-section for the hard process. Let me just leave that aside. What's left is the probability for emitting that gluon as the quark exits the reaction. And that probability is equal to 4/3 alpha s over pi, the integral dz, the integral dpt squared, and I left it out here. Once again, dpt squared pt squared over pt to the 4th, it leaves a logarithmic integral over pt squared. And with the same momentum structure, 1 plus z squared over 1 minus z, that we found in the initial state case. So once again, an alpha s, a log q, so this is an order 1 effect, and the order 1 effect is radiating a collinear gluon every time I produce a hard quark out of a hard process. And I think you can see some other features of this. This is the quantity which is the gluon momentum fraction. So there's also a soft singularity here. It's very much more probable to emit a soft gluon as we saw, either from a quark or from a gluon when it splits. And secondly, this is a process that is order 1 in QCD, and in principle we have to consider it not only in the first order, but in all orders of perturbation theory. So now we need some equations that would sum up multiple final state gluon emission, where again the transverse momenta here of these gluons are strongly ordered. PT, whatever is the Q here, PT1 is smaller than that, PT2 is smaller than that, etc., in order to get an order 1 effect. If you like, you could try to sum this whole set of emissions using a formalism very similar to that we used for the parton distribution functions. So we could, if we wish, define something that you would call a fragmentation function. So let f sub f of z dz be the d probability to find a quark, flavor f, of momentum fraction z from a final state quark of some particular momentum, of momentum p. So roughly, the quark of momentum p is emitted by the hard process. Lots of things are emitted here. Out comes a quark of momentum zp, and the fragmentation function gives the probability that this particle is present. Similarly, we can define fragmentation functions from an initial quark for antiquarks and for gluons. And actually, I probably should write that because there are fragmentation functions also for gluons, turning into gluons, quarks, and antiquarks. In fact, these fragmentation functions, basically because this expression is identical to what we derived before, excuse me, satisfy the Alterelli-Parisi equations. And so let me just write one for an example. D f sub f to q of z d log q is equal to alpha s of q over pi, the integral dz over z. The same Alterelli-Parisi splitting kernel, q to q, f sub f of, oh, I should call this w maybe, z over w, plus the splitting from a gluon to a gluon, f gluon of z over w. And all of these fragmentation functions, again, are functions of q. Okay, well now you can go on and integrate these equations, but I think the more interesting thing to do is to ask what is the qualitative effect of these equations. And that's actually something that is extremely nice. If I start out with a hard process that produces a quark, the first thing that happens, and it always happens, the probability is order 1, is that the quark emits a hard gluon in the collinear region. Then the gluon might emit 2 more gluons. The quark might emit another gluon that splits to a quark and an antiquark. It keeps emitting gluons, and everything starts emitting gluons, quarks, and antiquarks. Actually, because of the large coefficients in front of the gluon to gluon splitting function, most of what comes here is gluons. But what you see is that what we get is a kind of a multiplication of particles in a cone whose size is determined mainly by the initial radiation in this process, which then turns into a shower of quarks, antiquarks, and gluons, all moving roughly collinearly in order to take advantage of where the probability is maximized. Then, when the momentum transfers get really small, the soft part of QCD takes effect. You have quark confinement. quarks and antiquarks that are nearby pair up and make hadrons. And what you end up with at the end of this process is a shower of hadrons, all moving roughly collinearly with one another and carrying, as you see, the total momentum that was in that original liberated quark. So this is the thing that in the first lecture we identified on event displays as a jet. And now I've given you, at least to first order in QCD, a detailed theory of the way that jets are formed as a process that goes from large momentum transfer here to small momentum transfer there. So I think now we see a number of interesting things. We've understood much better the nature of the parton distributions of a proton. We've understood that those evolve with Q, an effect that's absolutely necessary to take into account in any calculation. And we've seen that experiment actually agrees with the predictions of QCD for the qualitative features of that evolution. We've also seen that when you produce quarks and gluons from QCD hard processes, they naturally are materialized as showers of quarks, gluons, and antiquarks, which, after quark confinement, become showers of collinearly moving hadrons, the jets. So in the first lecture I told you the jet is the observable manifestation of a quark or a gluon. Now I've told you in a very explicit way that's the prediction of QCD. So now we're in great shape. And now I think we're in a good position to actually understand what events look like at the LHC. So that'll be the topic of the next lecture. Thank you very much. Okay, any questions I can answer at this point? Yes? Please.
Okay, in this lecture we talked about fragmentation and so on, but after fragmentation we need to make some hadronization, and how people to solve this problem.
So I should say from a fundamental point of view, it is not understood how quarks and gluons form hadrons. The only thing that's understood about it is that the momentum transfers which are involved are small. And so you can make various hypotheses about how to do that. So these hypotheses actually come with people, and they come with even particular computer programs that attempt to model high-energy hadronic interactions. So probably the two most commonly used simulation programs for high-energy reactions, both E plus E minus and PP, are called Pythia and Herwig. Pythia is a product of the Lund University in Sweden. Torbjörn Sjöstrand is the leader of the group. And Herwig is a property of Cambridge University. And Brian Weber, I guess, is the longtime leader of that group. In Pythia, what they do is they, at a certain point, so at a Q of about, here, let me clear some space here. A Q of about 3 GeV, they consider the spectrum of quarks and gluons which are present after the simulation of this QCD cascade process. The gluons are split into QQ bar, and then each pair of particles is joined by a color string. And then there's a model for the breaking of the color string into hadrons, which actually Bo Anderson, the founder of this program, was the inventor of that model. In Herwig, it's somewhat simpler. They go down to Q about 1 GeV. Again, you get quarks and antiquarks as the result of the cascade. And then basically you just pair up these particles into mesons. You try and identify them with objects in meson spectroscopy, and you decay them in the right way. Of course, here also, you have to eventually use meson spectroscopy and baryon spectroscopy and decay things in the right way. And so what happens is you introduce a very large number of parameters. You use the data in the particle data tables to determine some of those parameters. You fit other parameters to the, mainly to the detailed properties of jets, you know, how many sigmas, how many lambdas, et cetera, that comes from the LEP data. And so eventually you come to a more or less purely phenomenological description of the hadronization process. And actually, there are detailed exceptions, but mainly these two programs give the same qualitative results for what events look like, which shows you that really you're not sensitive to the exact mechanism of hadronization, but mainly just sensitive to fitting the data of, again, a certain corpus of events to explain the data in another corpus of events. Okay, other questions? Okay, we meet again this afternoon for lecture 4, so I'll see you then.